Hello everyone, my name is John McCarthy. I'm a second year PhD student here in Tyndall National Institute. I work for IPIC as a part of the Integrated Photonics Group. My presentation today is going to be on designing photonic integrated circuits. So how this talk is going to go is first I'll run through a few laser fundamentals, then I'll talk about some laser designs like a Fabry Pro, a slot Fabry Pro, and an MMI structure. So what are lasers used for? Modern optical networks employ hundreds of different lasers which fill up the emitted bandwidth. These optical networks involve hundreds and thousands of kilometers of optical fibers underneath the ocean floor, connecting country to country and continent to continent. Light wavelengths transmit more information per second than sound, and with a stronger signal. So lasers are quite attractive for high-speed telecommunications. A photonic integrated circuit, or PIC, is a device that integrates multiple photonic devices or structures on a single chip. PICs are used to generate and to manipulate light and produce information signals imposed on optically wavelengths typically in the visible to near infrared range. The primary application for PICs is in high-speed telecommunications, though they also have applications in other fields like biomedical and photonic computing. So here is an example of a very simple laser structure. The active region of the laser would be made up of multiple layers creating multiple quantum wells. One such quantum well is shown here. It's made up of two layers of indium phosphide separated by a layer of InGaAsP. So what this does is it creates a double heterojunction here, which effectively creates a quantum well between the band gap energies of the layers. So when forward current is applied, the electrons flow along the conducting band and are confined within the quantum well structure here. Electron-hole recombination occurs and a photon is emitted with a wavelength equivalent to the band gap energy. Typically, lasers are fabricated with highly reflective surfaces known as cleaved facets. That's shown here and here. When current is pumped through the gain media, the majority of the photons are initially confined in the active region by the cladding and cleaved facets. So the cladding layers are up here and down here. These cladding layers have a lower refractive index and can therefore reflect the photons back into the active region. The gain medium of the laser will only amplify light over a certain range of wavelengths, corresponding to the laser's gain bandwidth. Depending on the wavelength of the photons and the cavity length, the reflected photons will either interfere constructively or destructively. After one full oscillation, the photon will have traveled a distance equivalent to twice the cavity length. If this distance is an integer multiple of the wavelength, then the wave undergoes constructive interference. If not, then it goes under destructive interference and is cancelled out. One objective when it comes to high-speed telecommunications is to have a laser that generates a single mode. A single mode of a laser is described by its side mode suppression ratio, or SMSR. Now what that is if you plot the power spectra of the laser in dBm, the conversion is shown here, the difference between the dominant mode and the secondary mode in decibels is the SMSR value. So what dBm is, it's basically a logarithmic scale compared to the power ratio. So if there was a difference of 0 decibels, then the power ratio would be 1. If it was 10 decibels, then the power ratio would be 10. And if it was 30 decibels, then the dominant mode would be 1,000 times more powerful than the secondary mode. So for a laser to be considered single mode, we want the SMSR to be 30 decibels or greater. Now I'll move on to laser types. So the simplest type would be a Fabry Pro. So this is quite similar to what I was talking about earlier. It consists of a cavity with highly reflective surfaces at each end. The light produced in the cavity bounces back and forth, forming a standing wave. The output mirror always transmits a constant fraction of the light while reflecting the rest back into the cavity. So here's just a simplistic view of one of the ridge lasers we produce in Tyndall, We'd initially start off with just a wafer made up of all the layers required, and then we just etch out the ridges. Then we coat that with metal, and by pumping current through it, that's what generates light. A useful thing to simulate would be the reflection profile of a laser. So transmission matrices can be used to describe the transmission and reflection of a laser and how it varies with wavelength, therefore allowing one to simulate the wavelengths confined in the cavity. So there are two main types of transmission matrices. There's the transmission matrix to describe a reflection. This takes into account the change in the effective refractive index. And then there's the transmission matrix to describe a waveguide. This takes into account the length of the waveguide, the refractive index, and the wavelengths involved. So in the case of a Fabry Pro, we have two reflections, or reflective surfaces, separated by a waveguide. So we just find the cross product of those three transmission matrices, and this results in a 2x2 matrix. We can get the reflection profile by dividing T21 by T11 and squaring it. So in the case of a Fabry Pro that's 600 microns long, if we plot that reflection profile against wavelength, this is what we generate. So the maximum peaks represent the wavelengths that can be supported or lased by the laser. Here I'm showing the exact same thing, however I'm showing how it varies with the length of the Fabry Pro. So as you increase the length of the Fabry Pro, we get more and more modes. I said earlier that the gain media of the laser will only amplify light over a certain range of wavelengths, and this corresponds to the gain bandwidth. So in the previous simulation I was able to generate all these modes, however not all those modes would actually be generated by the laser. Instead, the gain bandwidth of the laser would amplify the ones generated and suppress the ones that are not, as you can see here. So the longitudinal modes are equally spaced by a frequency difference of the speed of light divided by twice the cavity length. And only the modes whose corresponding frequencies fall in the laser's gain bandwidth will be amplified and lased out. Here is an experimental value of such a Fabry Pro. So here's a Fabry Pro with a length of 700 microns. As we saw in the simulation, we get multiple of these equidistant modes. However, instead of them going on for infinity, they're actually suppressed and amplified by the gain media of the laser, as you can see here. What we can also determine is how the power output of the laser varies with the length of the Fabry Pro. So as you can see here, with blue being 600, green 700 and red 800, as you increase the length of the Fabry Pro, the threshold current of the laser decreases. What the threshold current is, it represents the point where the laser changes from spontaneous emission to simulated emission, or when the laser begins to laze. The length of the Fabry Pro also affects the actual power output of the laser. So the longer the Fabry Pro, the more power you get. When integrating a Fabry Pro laser into a photonic integrated circuit, we don't typically use the two cleaved facets. Now granted, in a PIC we'll definitely need one cleaved facet to actually measure, well, at least one cleaved facet to measure the actual output of the device. However, sometimes the Fabry Pro would be in the center or at the very end of the device, and their lengths won't correspond it or allow it to be stretched to the cleaved facet. So we have two separate alterations here. One involves etching down into the wafer excuse me, further than the ridge, but through the active region. This is what's called an etched facet, and the idea is this etch alone would be reflective enough to confine the light within the laser. A more effective method is using a metal etched facet. Now, the metal etched facet does reflect light better, and as you can see here, it has a lower threshold current and higher power. However, it prevents light from passing through, and sometimes when we're injecting light from one laser into another, we do need that, so that's why the etched facets are useful, even though power-wise they're more weak. Now moving on to a slotted Fabry Pro laser. So a slotted Fabry Pro laser is similar to that of Fabry Pro, except we etch these slots into the ridge of it. So this is an easy method to produce a single mode. These slots act as reflective defects, causing partial reflections in respect to the changing effective refractive index, as you can see here. So what this represents, this is just a side view of the laser. The top is the ridge, the blue is the wafer, the dark red is the active region. So as light propagates along the active region, when it comes to a spot where the effective refractive index changes, a partial reflection occurs. So multiple regions where this partial reflection occurs is set up, and this could warp the shape of the reflection profile of the laser. Here's an example of just how it warps. So on the image of the left, it's similar to what I showed you earlier. It's the reflection profile of a Fabry Pro that's 800 microns long, has multiple modes, none dominate over the other. This is the amount of wavelengths that are confined in a cavity. However, when we introduce these slots, as you can see here, I introduced 8 slots with an interslot separation of 108 microns. Now what this did is these smaller modes, which were initially generated by the gain length of 800 microns, are suppressed by the larger modes created by the slots. So the idea is that a single mode spectra can occur at any one of these larger modes. However, whether or not it lasers here depends on the position of the smaller modes within. So there are 2 ways we can actually affect the position of the modes. One is we can move the position of the larger mode, or we can move the position of the smaller mode. Both are done by biasing the effective region. So the smaller modes here are generated by the Fabry Pro. By biasing the Fabry Pro, or sending current through the Fabry Pro, you actually change the effective refractive index and artificially increase the optical path length of the device. This is enough to change the position of these smaller modes. The same is said for the gain or the slotted section. As you pass current, you change the effective refractive index, and so the larger modes can be changed. When one of the smaller modes, or the maximum point of the smaller mode, reaches the maximum point of the larger mode, it dominates over the others, and the laser lasers at that wavelength. So, we begin with just a simple wafer. This wafer involves all the layers we need to create a laser, including the active layer, somewhere in the middle. So what we do is we exposing just this ridge section, and we remove the slots in between. So here is the gain section, or Fabry Pro section, and here is just the slotted section. Then you etch further at the end. This is to create the metal etched facet by adding the metal, as so. So the metal etched facet here allows light to be confined better within the Fabry Pro and the slots. Then there's a cleat facet here where you can measure it out. Also, oxide and metal is evaporated onto the top and sides. This is to create contact pads, so it's easy to probe the laser and send current through it. Here is an image of my setup in Tyndall. So, the device is placed on the chuck here, on the probing station. This is viewed through the digital camera. The power supply is used to pump current through the lasers, or, well, to the probes. There's needles at the end of these probes, and that's what you stick into the contact pads. Light is generated and collected into these optical fibers. The power is measured using a power meter, but it can also be sent to the OSA, and the spectra would be measured. I also have additional power supplies here for more complex devices. So here's a schematic design of my laser, and a more to scale design. So the gain section is here, that's 800 microns long, and then there's the slotted section made up of multiple slots with an interslot separation of 108 microns. And then there's these contact pads used to probe the device. So when I'm testing it, I probe both the slotted section and gain section. Current is swept through both of these individually. So let's say gain section is kept constant at 10 milliamps, the solid section goes from 10, 11, 12, 13, and the spectra is measured at each time. When it reaches the end of its cycle, then the gain section changes from 10 to 11, and it goes through the cycle again. So at each cycle, the spectra is measured through the cleaved facet. With each of these measurements, 2 points are taken, the SR measured, the SMSR and the lasing wavelength. So as you can see, along the bottom here is the current across the gain region, or the Fabry-Pérot region, and then along the y-axis is the current across the solid region. The color represents the SMSR detected during that region. And down here, instead of SR, I have the equivalent wavelength. So as you can see, we get multiple regions where the side mode suppression ratio is 30 decibels or greater. So the laser is effectively single mode. However, down here, we can see that this single mode nature occurs at multiple different wavelengths. So the laser can also be described as tunable. Here's probably just a more easy to envision diagram. Here is an image of all the lasing wavelengths plotted together. So each color is a different single mode wavelength. So 9 wavelengths were generated with a side mode suppression ratio of 30 decibels or greater, and this was across a tunable range of 27 nanometers, which is quite good for an integrated laser. So I've just changed all the experimental data to red that I showed earlier, and then I'm showing the theoretical reflection profile that I showed earlier plotted against it. So as you can see, they're both in good agreement. The experimental data was detected at the maximum point of the modes that the theoretical data suggested. So the final laser type I'm going to talk about is the multimode interferometer. So here's a simple example of an MMI. An MMI is typically named after the number of inputs by the number of outputs. So this would be a 1/2 MMI. MMIs are useful. They're quite effective at splitting light equally into multiple waveguides. So as light propagates here, half the power would go through here and the other half would go through here. This is useful, for example, if I had a photonic integrated circuit and I wanted to know how the spectra looked at a specific point before it was meant to go into another device, I could just use an MMI to split the light and then take this to a cleaved facet and measure it there. And then what's measured there should be similar to what's actually going into the device. Yeah, or they could just be useful if I want to split light into 2 separate devices, which I also do. So here's the fun image showing how the light propagates within an MMI. So as you can see here, light propagates in through this input, and then there's 2 different outputs where the power of the light is half of the input. So as the light enters the MMI, it splits and propagates and eventually recombines in certain areas. The light in the MMI is very width and length dependent. So depending on the width, I should say, it also depends on the length of the MMI. So for example, if we wanted a 1 input 3 output MMI, however with the same width as this, you can see that the 3 outputs would be located here, here, and here. And if we wanted a 1/4, we'll locate it here, 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 and here. So the more outputs you want, the smaller the device would get. If you actually increase the length of the MMI to double this length, then all the light should recombine and you can have 1 output. It's just the phenomena of the MMI. It's quite interesting, in my opinion. So the reflection profile of this such device would resemble what I showed here. So, in terms of experimental analysis, what one typically tends to do is keep the gain section constant. I believe I kept it at like 60 milliamps, and then vary the current across arm 1 and arm 2 and measure the output through the output arm. So here is some results I got from that. So I vary the current from arm 1 from about, that's actually quite low, yeah, about 1 milliamp to 70 milliamps across both arm 1 and arm 2. So the SMSR instantly was excessive. It achieved its 30 decibel requirement, and then it created this pattern-like structure, just showing how elegant an MMI actually is. They aren't typically square or comparable when generating from arm 1 and arm 2. That's because the lengths of arm 1 and arm 2 are different sizes, so the optical path length wouldn't have been changed sufficiently or equivocally. Here you can see the different wavelengths generated. I think this might have been less tunable than the slotted one I showed you earlier. Yeah, it is. However, all these wavelengths were produced with a high SMSR with very low current input. So that is all I have to talk about my aspect of the monolithic and heterogeneous integration part of IPIC. I welcome any questions if there are. Thank you.